in the chat through type questions for your questions for David. Before we get started, as usual, you're hearing my voice and you'll be hearing David's voice in English classes stage. The slides for the presentation itself will be, we will continue to type in classes chat as we are now. Just above classes chat is student presentation, the channel student presentation. This channel is open so far only during student presentations. Regos has tagged that. Everyone take a moment, make sure that you can see student presentation. In fact, this would be a good time to go there. At the bottom is a slide entitled Largest Star. Above that are all the slides from previous student presentations. Everyone make sure that you can see, that you can join the channel student presentation. You should join us there now. You should see the first slide of David's presentation entitled Largest Star. I want to give everyone a moment to get there. We should all be in the channel student presentation. Let me give everyone a moment to get there. And everyone, Jaspreet, thank you for that. Everyone should now be able to see the slide, Largest Star. Perfect, Jaspreet, thank you. Let me give everyone a moment to join the channel student presentation. We will continue to be speaking here in English classes stage. There may be some typing that continues in classes chat, but you want to be watching the channel student presentation. We'll be starting in about 30 seconds. I'm looking at classes chat right now. It looks like everyone is able to see student presentation, as Regos indicates. If anyone else has any problems, let us know. For students who are new, take a look at the channel classes FAQ. That will give you the information about how to join classes, permissions and roles that are needed. How normally to join the stage. Today will be only David's presentation. And it looks like we're ready to go. Okay, student presentations are the opportunity for students to both practice their English skills and present to the class topics of such interest. This is the return of David Davudian. We're so fortunate to welcome David back. His first presentation was so popular, Our Limit in the Universe. Today, David will be continuing his series on the universe. Today's presentation is entitled The Largest Stars in the Universe, Their Life and Death. Everyone, a huge round of applause. In your thoughts, we'll return to classes chat after the presentation. Some of you are still in the chat. In your thoughts, a huge round of applause for David. When the presentation is over, we'll do the actual applause, as some of us are doing in the chat. It's never too late to add some applause. David, if you're in the chat, you can see those applause now. Everyone, join me now. Let's switch over to student presentation. And everyone, welcome David. Whenever you're ready, and remember, let me know when you're ready to go to the next slide during your presentation. Everybody, a big welcome to David. David.
Hello everyone, and welcome to my presentation. Now, this presentation, as Mr. Allen said, is about the largest stars in our universe, their lives and their deaths. Now, before we go on, normally I would say that in the end, but I'm just going to say it from now, just so I wouldn't forget. None of these slides are made by me, and there is a video at the end that's not made by me, so just to clarify that. Sir, please, go ahead and move on to the next slide, please, Mr. Allen. First of all, things that would like to be stars. The smallest things that have some sort of star-like matter are sub-brown dwarfs, like Jupiter. Move on to the next slide, please, Mr. Allen. Jupiter is made up of the same stuff that make up our sun, just much less of it. Now, if you were to take 90 Jupiters, move on to the next slide, please, Mr. Allen. If you were to take 90 Jupiters and threw them at each other, it wouldn't be enough to create a star. However, it would be enough to create something else. A brown dwarf. What is a brown dwarf? A brown dwarf is a glowy gas giant that doesn't fit into any category very well. It's not it's not hot enough and bright enough to be a star, and is too massive to be considered a planet. So it's some sort of abomination in the middle that is a huge disappointment to the universe. Now, interestingly, move on to the next slide, please, Mr. Allen. Interestingly, if you were to add more mass to a brown dwarf, it wouldn't make the brown dwarf bigger, just its insides much denser. Now, the denser the insides, the hotter the insides. Thus, the more fusion. The core starts to fuse any particles of energy like helium and hydrogen that it can find. Now, that means that by adding more mass to a brown dwarf, we wouldn't make the brown dwarf bigger, it would just make it glow a little. So, someone may ask, how can we turn a brown dwarf to a star? Move on to the next slide, please, Mr. Allen. Once a certain mass threshold is reached, the brown dwarf, or any gas bubble, a star or a brown dwarf, will be hot enough to fuse helium into hydrogen, aka it starts to burn fuel. Once you have the fusion of helium into hydrogen, you have yourself a star. Now, the more massive a star is, the hotter the insides of the star is. Thus, the more fusion and the brighter. Now, enough talking about some glowy gas giant, planet, wannabe, whatever it is. Let's talk about true stars. The stars that make up our night sky. Move on to the next slide, please, Mr. Allen. Main sequence stars. Now, main sequence stars are the stars that make up our night sky. Most of the stars you see in the sky are main sequence stars, including our sun. Now, what does main sequence mean, you may ask? To understand that, we need to understand a star's life. Move on to the next slide, please, Mr. Allen. A star's life is divided into 4 phases. First of all, birth, then the main sequence phase. Once the main sequence phase ends, the giant phase kicks in. After the giant phase, death comes to a star. Birth is star's life in which the gases of the universe come closer and closer to each other and form gas bubbles. These gas bubbles go on to turn to either planets, which is a different subject from ours, or stars. When they turn into stars, they start to fuse helium into hydrogen. They start to burn their fuel. Thus, their main sequence phase kicks in. So, the main sequence phase of a star's life is the phase in a star's life in which the star burns its fuel. Once the star runs out of fuel, the giant phase will kick in. We'll talk about the giant phase later on in the presentation. For now, let's move on. After the giant phase, death comes to a star. Now, death can come in 3 ways. 2 natural ways and 1 very uncommon way. The 2 common ways are either by simply fizzling out or by dying in a core collapse supernova. The uncommon way is a collision with other space objects, such as neutron stars, other stars, and or being swallowed by a black hole. Now, because space is so massive, these things don't happen that much. However, needless to say, it does happen every now and then. Move on to the next slide, please, Mr. Allen. The smallest stars that we've managed to find are red dwarfs. Red dwarfs are barely massive enough to fuse helium into hydrogen. Thus, they are very dim, not very hot, and very small. However, because they are not very hot and very dim, they burn their fuel very, very slowly. Because they burn their fuel very slowly, they have stupendously long lives. Because they live long lives, they are the most abundant star in the universe. Move on to the next slide, please, Mr. Allen. One of the closest stars to our solar system is Bernard star. Bernard star is a red dwarf. As we said, red dwarfs are very dim and very small. So it cannot be seen in the night sky, despite being one of the closest stars to our solar system. Whilst a star like Rho Cassiopeia, which is 3,500 light years away from us, can be seen with the naked eye in the sky almost every night. However, as we said, they live very long lives because they are very dim and not very hot. Bernard star will live approximately to 10 trillion years. That will outlive our sun by trillions upon trillions of years. Speaking of the sun, let's introduce a familiar face. Move on to the next slide, please, Mr. Allen. The sun is 300 times brighter than Bernard star, and it has 7 times the density of it. However, because it's more massive and brighter, it's hotter and brighter, it lives a shorter life. Whilst Bernard star will live up to 10 trillion years, our sun will at most live to 10 billion. Now, that's still a lot for us as humans. However, for the universe, that's just a blink of an eye. Anyways, can we go even bigger from the sun? Of course we can. The sun is not a very big thing in the universe. Move on to the next slide, please, Mr. Allen. Sirius is one of the brightest stars in the night sky. On some occasions, sometimes in the year, it is the brightest, in fact. Sirius is a blue star. However, it is a baby blue star. It hasn't been there for a while. It has just started to burn its fuel. I say just started. Of course, for us, that's a long time. It has been burning its fuel for approximately 100 or 1,000 years. It's just that for us, it's a lot. For the universe, it's nothing, once again. So, it's not fair for us to compare a baby star to the sun. Let's compare 2 adult blue stars to the sun. Move on to the next slide, please, Mr. Allen. 2 such massive adult, if you will, blue stars are the Beta Centauri stars. The Beta Centauri stars are the opposite of Sirius. While Sirius is a baby and it has just started to burn its fuel, the blue Beta Centauri stars are quite old. In fact, they are running out of fuel to burn. Now, the Beta Centauri stars are massive. And because they are massive, once again, they are hotter and brighter. So, whilst our sun will live up to 10 billion years, the Beta Centauri stars will live to 2 billion at most. If not, they will get into their giant phase and they will collide with each other and either merge or destroy each other. That's a different subject, and we haven't seen any stars die in that way, so we cannot be sure yet. But, is this the meta? The more massive a star is, the hotter it is, the hotter the brighter the shortest life is. Well, let's try to figure out together. Move on to the next slide, please, Mr. Allen. The most massive star in the universe that we've managed to find so far is R136A1. Stars like R136A1 are strange stars. In fact, they kind of break the rules of star formation. You see, they are so hot that their solar winds too strong, stronger than they should be. So, because their solar winds are too strong, they are blowing the outer layers and the atmosphere of the star away. Yes, stars have atmospheres, it's just that they are very, very thin. Anyways, so by R136A1 blowing its outer gases away, it cannot have a giant phase. So we don't know how will the star die. And someone may ask, if it's breaking the rules of star formation, how is it there? That doesn't make sense, does it? Well, we don't know. However, the most likely answer to that is that stars like R136A1 are formed after the merger of 2 or more stars. However, at the end of it all, we don't know. Now, every second, R136A1 is blowing approximately 5 billion tons of matter away every second. So, Someone may think, oh, it's just going to blow itself apart and disappear. Well, because R136A1 is so massive, it can make up for any lost ground. If it loses 100 billion tons, it will just make up for it because it has so much mass. So we don't know how to die. However, we're not here to talk a lot about their deaths. We're here to talk about what is the largest star. So, what is the trick to going bigger from here? We can't add any more mass to a star. It would just destroy itself because it cannot balance itself. Well, to go even bigger from here, we have to kill the stars. Move on to the next slide, please, Mr. Allen. Now, before we go on to red giants, let's talk about the giant phase of stars. You see, in the first place, why does a star burn its fuel? To produce energy. That energy counteracts gravity and the outer layers of the star. You see, gravity and the outer layers of the star are constantly pushing against the core to try and destroy it. So the core fuses helium into hydrogen and releases a lot of energy to counteract gravity and to hold the outer layers at bay. Once the star runs out of fuel to burn, its main sequence ends. And so, the outer layers and gravity of the star start to push against the core, melting it into a hot blob of plasma and lava. Once that happens, the core starts to panic. So it starts to literally cannibalize itself in order to survive for as long as possible. Now, burning fuel is one thing. Burning an energy-rich core of a star is another. The tremendous amounts of energy which is released from the core counteracts gravity and neutralizes it. All good. However, the outer layers cannot be neutralized. They are the shield of the star, and the star doesn't want to destroy its own shields. So instead of destroying them, the energy swells the outer layers. And so the star becomes hundreds upon hundreds of times its radius. One such star that has been burning its core for quite a while is Gacrux. Next slide, please, Alan. Gacrux is 30% more massive than the Sun, and it is still 84 times its radius. So it doesn't have that much mass, and yet it has a lot of size. Its size is massive. So from that we understand that a mass of a star is calculated by its core, not by its entire layers, because its entire layers are just blobs of plasma that don't make any difference. They can just be stretched out into something even bigger. Now, when our sun has its giant phase kick in, it will go even bigger than Gacrux, 200 times its current radius. It will swallow the inner planets of Mercury and Venus, and it will burn Earth and Mars to ash. So we should really think about getting away from the sun, because it really wants to kill us. But anyways, that's not our subject. Now, let's finally introduce the behemoths of the universe, the giants, hypergiants of the universe. Move on to the next slide, please, Mr. Allen. Hypergiants are divided into three categories: blue hypergiants, yellow hypergiants, and red hypergiants. Blue hypergiants being the smallest out of these three categories, and red hypergiants being the largest. The most well-studied of the blue hypergiants is Pistol Star. Now, why is it called Pistol Star is because the star formation in which a Pistol Star is in forms a pistol-like shape. I know, humans are very imaginative. But anyways, Pistol Star and other hypergiants are solar system-sized behemoths that are blowing themselves apart. So, whilst R136A1 is losing about 5 billion tons of matter every second, these stars, these hypergiants, are losing trillions upon trillions of tons of mass and matter every second. And yet, it is nothing. They can just make up for any lost ground. Now, even bigger than blue hypergiants are yellow hypergiants, like Rho Cassiopeia, the most well-studied of the bunch. We talked about Rho at the start of the presentation and how you can see it in the night sky almost every night despite being 3,500 light years away. Now, move on to the next slide, please, Mr. Allen. Rho Cassiopeia is massive. If you were to replace the sun with Rho Cassiopeia, it would swallow the Earth. and we would be very dead, needless to say. However, they are very rare. Yellow hypergiants are very rare stars. Only 15 of them are known to be in the universe, or at least the amount we've managed to find is only 15. What does that mean? Well, that means that a yellow hypergiant is just an intermediate stage. From here on out, stars like Rho Cassiopeia will either become a smaller blue hypergiant or swell into a bigger red hypergiant. Speaking of which, move on to the next slide, please, Mr. Allen. Let's finally introduce the true giants of the universe, the largest stars of the universe. Now, the boring answer of who is the winner of this contest is that we don't know. We know that red hypergiants are the largest category, but we don't know which of the red hypergiants is the largest. Because red hypergiants are constantly blowing themselves apart, they don't have a shape. They're just a hot, bright blob of plasma floating through space, so calculating that is really hard, to say the least. However, one of the largest, and the one which is thought to be the largest star in the universe, is Stephenson 218. Move on to the next slide, please, Mr. Allen. Stephenson 218 was probably born as a main sequence star, about tens of times the mass of the Sun. However, by now it has lost half of its mass. Thus, it is approaching its end. Now, Stephenson is big. Words cannot describe how massive this thing is. The same thing with Rho Cassiopeia. So let's try to understand it together. Move on to the next slide, please, Mr. Allen. If you were to replace the Sun with Stephenson, it would swallow Saturn and Jupiter. If you were to orbit Stephenson once at light speed, it would take you 8.7 hours. If you were to do it with the fastest plane ever created, it would take you 500 years. The Sun next to Stephenson is just a grain of dust. However, interestingly, move on to the next slide, please, Mr. Allen. Unlike other stars, Stephenson doesn't have 3 ways to die. It only has 2 ways to die. The first and the most likely to happen is that it will die by a core collapse supernova. The second way, which is highly improbable, is that it will die by collision with other objects. Any star that comes close to Stephenson 218 is just going to get eaten straight up. There isn't any star bigger than Stephenson so far. So any star that gets close to it is just swallowed instantly. However, it can die by collision with neutron stars and or black holes. And those are the only 3 ways for it to die. Well, 2 ways. Either by collision or, the most likely, by a core collapse supernova. Once that happens, Stephenson will give its gases back to the universe and restart the whole cycle once again. The cycle of birth and death. Now, if you want to experience this amazing journey one more time, without me waffling in the background, there is a video that I posted on YouTube. I didn't make, by the way. And it goes through this whole journey without the talking part. So, if you want to feel small and insignificant, feel free. Thank you, Mr. Allen. This is all I had, and I hope you all enjoyed it. I thought it would be very nice, and I really like space, so I decided to share my experiences. Yeah, Mr. Allen.
Everyone, let's take a look at the link to the YouTube video. Everyone, take a look at that link, and then after that, we will return to paste that again in the chat. The video, one student asked there in the chat, is the video one more time. Everyone, join me in classes chat. A huge round of applause for David. A huge round of applause. Back in classes chat. Back in classes chat. We are so fortunate to have the expertise and the presentation skills of David Davudian for his second installment in his series on the universe. Our student presentations are such a great opportunity for students to both practice their English skills and to present topics of such interest. In our classes, this is the most important aspect, our warm, supportive environment. We do that with our applause. To students who are new, that is what we're doing right now. Our applause is the way that we let each other know that you're doing a great job, the way we offer warmth and encouragement. Returning students have learned so well. It's so much more than just something that makes us feel good. It is fundamental, foundational to learning itself. This is the most important aspect of our community, our warm, supportive environment. David, what another extraordinary presentation. What an extraordinary presentation. David's visuals are so great. David's presentation skills are so advanced. I'm sure that as part of the question and answer that we will have in the chat in a moment, as we did for David's first presentation, we will hear the request to return for the third in the series. On the Notion page, you are able to see a list of past student presentations. We have seen such a great variety of those. We started with the very first presentation was a group of students presenting on English in their respective countries and advice to students. We followed that with poetry readings. David then gave his first presentation on the universe, our limit in the universe. Ninive, who again, a big thanks to Ninive for recording the presentations going forward, and she will be providing a recording of this presentation in this class. Ninive gave her amazing presentation on motivation and stress, that topic that is so important to so many of us. Cat Zero gave us our first student speech, Cats and How They Improve Our Lives. Students are welcome to give a longer, more formal student presentation, such as David is doing now, or if you prefer something a little shorter, more informal, you can do a student speech. Cat Zero gave us our first student speech, Cats and How They Improve Our Lives. And then most recently, before David, Gabriella, that great presentation on those such important words in English, connectors and linkers, and their importance in speech. Some of those presentations, as you can see on the Notion page, the link I sent in the chat, you will see the links to the videos that we do have. And once the Ninive has processed the video for David's presentation, we will add that to that page that lists previous student presentations. Demonade followed up with a presentation on our new Notion page, and we have a video of that as well. Under class schedule itself, towards the top of the new Notion page, you can see upcoming student presentations. And on the page, the link that I sent out, you can see the past ones. David, that was such an extraordinary presentation. Everyone, join us back in classes chat. And what we will do now for the rest of class, is take your questions by typing them into the chat, questions that you have for David on today's presentation. If you have questions remaining from David's first presentation, or topics in general about David's experience in the universe, or putting the presentation itself together, we would welcome all questions. You can type your questions into the chat. Again, we're back in classes chat. And we're taking questions about David's great presentation. The largest stars in the universe, their life and death. Questions about the universe in general. And we will be watching for your questions in the chat. Can see several people typing. We'll wait for those questions. While we're doing that, David, tell us again a little bit more about where you found your slides and a bit of your background, your interest in the universe, how you came to develop that interest, where you have found the background information that you presented today. Give us a little bit of your background, your interest in the universe.
I don't really know how it started. I saw a video on YouTube, then another, then another, then another. Eventually, I got really interested in it, and I saw the student presentations, and I thought maybe if I share my experiences and what I like, maybe someone would like it as well, and I would spark an interest in them. And yeah, so I found this channel. It's called Kirk's Arts. Very big channel, very good channel as well. I really like their animations and their video topics. So I thought to myself, I can probably make somewhat of a presentation by just simply taking screenshots, adding notes of my own and or from the video itself. And yeah, I just kind of got interested and came here to share it with you guys. And that's it. Here we are.
Thank you so much. And our first question, thank you, Jaspreet. Our first question, David, as you can see from Jaspreet, why does the size of the brown dwarf not increase after adding mass? Great question. Thank you so much, Jaspreet.
Well, adding mass is just that mass doesn't mean size. A star's inside is not filled. It's kind of empty. It's just filled with gases and the hot air. So when you're adding mass, you're not adding size to the outer layers which make up the star's size. You're adding material to the core of the star. So the core is getting bigger, but the outer layers of the star is not getting bigger. So the way we see it is that the star is getting heavier and not getting bigger. That's the reason.
Can you give us an idea? We hear that word so often, the idea of mass. Can you give us a further idea of mass itself, what we're referring to when we hear that important word?
Well, in our case, in space, when we're talking about mass, we're talking about gases, space dust, maybe an asteroid that finds its place in the wrong place and ends up crashing somehow into the core instead of getting burned in the atmosphere. Mass in space means anything that may add material to the core. That's how we work with it in space, or at least as much as I have managed to understand so far.
Perfect, thank you. And Skeleton, thank you for your great question. From Skeleton, David, doesn't hydrogen burn into helium when the stars burn? And Skeleton heard you say that helium burns into hydrogen.
Oh, maybe I said it the wrong way around. I'm sorry. I'm really sorry about that. The idea is that the star fuses helium into hydrogen. So from helium, it creates hydrogen. Not that it. Oh, I understand your question now. There isn't helium and hydrogen in the star. It fuses helium into hydrogen. It turns it into hydrogen. And then it burns it. That's how it works. I think.
Perfect.
If that's what you meant, of course.
Perfect. And Skeleton, let us know if that answers your question, or by all means, if you have a follow-up question to that. Thank you so much for that. Akai003, I love this question. You said you like space and universe stuff. What is the thing you're interested in? What surprised you the most? I love that question. In your study of the universe, such a broad, wide-ranging topic, such a literally endless topic. I love that question. What did you find you're most interested in, and what in your study of the universe has surprised you the most?
Well, I don't know. Is pathetic a? Can I use that in the in my
Sure,
answer?
sure,
Okay.
sure.
The thing that most surprised me in my learning in space is how pathetic humans are. That's the thing that surprised me the most. Instead of focusing on our survival outside and on exploring the massive amounts of size and areas and planets and stars and whatnot, instead of that, we're just sitting in Earth and squabbling amongst each other to control Earth, whilst there are millions, if not billions, if not trillions of planets just like Earth. We could probably fit every human into one planet, and yet we just don't care about the outer world. I don't know if it's just fear of the unknown that drives our countries and, well, our governments and whatnot to ignore space, but it is really depressing how pathetic we are, and we don't see the bigger picture.
Thank you for that. And that, of course, is such a deep topic expressed in through so many different senses, and that sense of the scale of the universe and the relation of the Earth to that scale is part of what David covered so well in the first presentation. Monk brings up a great thought, the idea of if we could reverse the flow of things, if we could turn CO2, which Monk goes on to more detail later, the sense of turning carbon emissions themselves back into oxygen. David, have you studied any of the biological processes? And in terms of the life of stars, in terms of life, organic life itself on Earth, have you taken a look at that? And do you have any thoughts on those biological processes and how those are a part of the birth and death of life of stars themselves?
I haven't gone into depth. I just seen two, I think it was articles we call them, or newspapers. It was about how we can use organic life to turn Venus, the most dangerous planet in the solar system, into Earth using organic life, and we can turn Mars, a cold desert, into Earth using also organic life. And well, we call it, I forgot the name of it. It was very good. Other than that, I haven't gone in depth about these things.
And again, the questions are always great questions. If some of the questions in particular, students would like to see a follow-up presentation, please let us know that in particular. We would love to have David come back for a third presentation. Continuing, Great Single has a great question about temperature. It's about temperature, and David, you've let us know in the presentation what happens in the life of stars with temperature. Can you tell us some more about the changes in temperature through the life of a star and the meaning of that to the life of the star, to the life of organic life on the planets that surround the stars? A little more about temperature, please.
Well, temperature, when it comes to stars, is connected to everything. Like heat, which is the most important thing in a star, is connected to everything except for maybe the size of the star. For instance, red dwarfs that we talked about. They are very small and not very hot when compared to other stars. For instance, Bernard's star, which we talked about in the presentation, has a temperature, an average temperature of 1,500, whilst our sun has an average temperature on the surface of 6,000 degrees. So the hotter, as I said in the presentation, the hotter a star is, the brighter it is, because the more fusion that happens in the core. So yeah, heat is very much connected with other aspects of a star's life. The hotter the star, the brighter it is. The brighter it is, the more fuel it burns, and thus the shorter its life is.
Perfect. Um, Et's question a little further down in the chat, a question that of course has become so recent to us all. And again, as we answer this question in all the things we do in our class, part of environment being the most important thing, we have the utmost awareness of a variety of backgrounds, a variety of ideas, and we are respectful of all of those different perspectives. We value so much, of course, the perspective of David, and this question itself, the existence, the questioning of aliens, that is life, organic or otherwise, that have been based, arisen on other planets. David, do you have thoughts on the existence of aliens?
Well, I spoke about aliens in the previous presentation. I'm gonna say it again. Life is a mistake. So, life on Earth was made by a mistake. The universe made a mistake by creating us. And that's why the universe is so inhospitable for us out there. It created us by accident, and it is currently using every single tool it can get to destroy us. Either by swelling the sun, by destroying the ozone layer, and we're really not doing ourselves a favor by destroying our own Earth, our fortress Earth. So alien life is highly improbable when it comes to the universe. However, there could have been similar mistakes in other places of the galaxy and or the universe. So whilst it's not completely impossible, I'd say it's 1 in a million chance that other life or other life forms are there in the universe.
And the great thing about our community, and I love seeing this in the chat, the rich, the enthusiastic discussion of so many topics. This one included. David, thank you so much for your thoughts on that. Continuing down, and that discussion is continuing. Let's go down to Jaspreet. Jaspreet, thank you for your next question. What happens when a star dies? Does it disappear by conversion of mass into energy, or does it turn into something else? And David, you may choose to incorporate that into your answer along with Crazy Eight's question, which follows. Does the death of a star relate to the formation of a black hole? Two great questions related to each other.
I'm gonna answer Jaspreet's first and then get to the other question, because that's a very good question, the second one. Stars that die, well, they don't disappear. You see, their gases are released into the universe. Of course, large quantities of those gases are burned and, as you say, disappear. However, even more amounts of gases and material just escape into space, and eventually, after trillions or millions, billions or trillions of years, it will become part of another star. So, for instance, once Stevenson dies, Stevenson 218 dies, its particles will live on in the form of another star that will be born later on. So, stars do not disappear. And the second question is a very good question. Stars that die sometimes, well, black holes in general are formed out of death of stars. However, some stars fail to turn into black holes, and instead they turn into neutron stars. Neutron stars are so massive that if they were just a little bit more massive than they are, they would literally turn into a black hole. So yes, death of stars are very much connected with black holes.
Okay, continuing, and Et, thank you so much for your
let me return to the chat. And Jaspreet, appreciate your comments on David's thoughts on our need to care for our planet. More questions?
One's question, David, is there, your thinking on, is there a chance of finding enough water for survival on Mars or other planets? Have you taken a look at the future, perhaps, of life on Earth on other planets?
Interestingly, yes, there are quite a lot. Well, not quite a lot. There is Saturn's moon, Triton. It has lakes. It has nitrogen water. Now, nitrogen water is different than normal Earth water. However, it's nonetheless water. So that's what I mean. Whilst it's highly improbable for aliens to live in those lakes, either be it bacteria or some sort of advanced species that lives underwater, nitrogen water is not drinkable and it does not support trees. So why would it support bacteria? Now, of course, maybe some bacteria adjusted and developed immunity to nitrogen water and was able to live there. So maybe in a few million years, if we send humans to Mars, to Triton, they, like the bacteria, will evolve and be able to live in very inhospitable planets. But that would take a long time.
Perfect. And Blazing Pickles, great question. Can you tell us about neutron stars?
Neutron stars. Well, a very, very long subject, that one. Maybe my final presentation, third and final presentation, will be about them. But for now, let's get into them a little bit. Neutron stars are very unstable things. For instance, every second a neutron star spins 10 times clockwise. Every second. So getting close to it is very, very dangerous. And unlike other stars, neutron stars are the size of cities. They're not massive. So like this, one neutron star is the size of New York City. They are very small and yet very strong, very dangerous, and as I said in one of the other questions, if you were to add any more mass to a neutron star, it would turn into a black hole. So it is very, very massive.
Neutrons, that brings up a question. Let me add a question to that. neutron stars, some of the new things that we're finding. I read a article recently of some recent discoveries of galaxies. David, can you give us a sense of the knowledge of the universe itself, how that has evolved over time? Were there points in history where there were rapid discoveries? Is that continuing at a rapid pace? Can we expect to find out more and more? What's your thoughts about the history of discovering all these amazing things of the universe? Have there been times in history where that knowledge has grown a great deal, more slowly? And what do you see in the future of the growth of our knowledge regarding the universe itself?
We are bound to get even better at at absorbing stars and finding new stars and galaxies. It's bound to happen. It's just a matter of time. However, when it comes to the past, we were very bad at it, to say the least. We thought there was a canyon on Mars that resembles a canal. We thought there were humans on Mars because we thought that canyon was a canal. So we were very, very bad at absorbing space back a few hundred years ago. In fact, up until the 1930s and 1940s, we didn't even know that Pluto existed. So we have come a very long way.
And following up to that last comment, and again, these topics provide for such rich discussion and different perspectives from so many. Jaspreet makes the comment, he doubts that humans will exist for that long. David, your thoughts on that? Do you feel that in time humans will develop additional ways to cope with the evolution of the universe, where things are headed? What is your thinking? What is your hopes for merely the physical, the organic survival, the challenges involved in that as the universe evolves for humans themselves? What's your thinking on that great question?
Well, as I said, we will not be here for a while. Well, it's a while for us as humans, but once again, our time is nothing for the universe. As I said, the sun will have its own giant phase. It will swell to hundreds of times its radius. It will either A, burn Earth to a crisp and fry us all to death, or B, it would just swallow Earth and leave nothing of us. So, unless we manage to find ways to explore, colonize, if you will, other planets in the galaxy and in the universe. No, if we just stay on Earth the same way we have been for the past 200 or so thousand years, we are doomed, quite literally. So yeah.
Perfect. Crazy 8 asks a great question, and let's look at that in conjunction a little further down. Smoker from India, Crazy 8's question: do you think we will be able to explore stars in the future? And Smoker from India's related question: do you think we will be able to travel to other solar systems or galaxies in the future? David, what do you think the future holds, both in terms of exploring stars, as Crazy 8 says, universes, galaxies, and solar systems, as Smoker says? What do you see in the future for how we will discover these things? Will we be doing our exploration from the Earth, from the Space Telescope? Do you see space travel coming in the future? What is your thinking on the future and our exploration and understanding of these matters?
Well, if we continue heading in the route we're going right now, it would just take us way too long as the sun takes for it to kill us. However, if we were to be serious and actually work on becoming a interplanetary, intergalactic civilization, yes, we're definitely able. And if we're lucky and there are alien lives, advanced alien lives out there, if we can establish diplomatic, for instance, diplomatic relations with them, if we can somehow speak to them, though it would be very improbable, we could, for instance, buy from them technology to travel at the speed of light, if that's possible. If the most likely thing happens and we are alone in the universe, that still is good. That means that humans have the whole universe for them to work with. It would just mean that, for instance, shows like Rick and Morty will not be truth. That's the only downside of it.
Perfect, thank you. Let me just mention to students who may have joined us late, we're doing a student presentation today. The Largest Stars in the Universe, Their Life and Death by David Davidian. This is a follow-up presentation to his first presentation on the universe. Student presentations in our classes are the opportunities for students to do a informal or formal, either student speeches or student presentations on any topics of interest to the class. You can do that working with your fellow students or on your own. The entire class today is one of those student presentations. The Largest Stars in the Universe, Their Life and Death by David Davidian. We saw that great presentation. We will have a video available. Thank you to Nina for that. Once that's processed, the link to that will be on the Notion page. We saw David's great presentation. We're continuing with questions and answers in the chat right now. We're now at Ra1's great question, and such a deep question. David, your thoughts. What things have you seen on this tremendous question? The age of the universe, your thoughts on the origin of time itself. What is time? Such a deep philosophical question. When the universe started, when did time exist? What's our understanding of time itself? Did anything exist before the Big Bang? And Ra1, you did a great job with your English of expressing those very large questions. David, your thoughts on time, existence before the Big Bang, your thoughts on those huge questions?
Before the Big Bang, there was nothing. Absolutely nothing. No time, no materials, no dust, no air, no nothing. Nothing. Absolutely nothing. No particles, anything. However, after the Big Bang, we do know what happens. You see, because light takes time to travel, we can glimpse back in time, quite literally like a time machine. For instance, we can see a galaxy that was quite recently discovered. It is 15 billion light years away from us. And it is the oldest galaxy we know. So, because light travels and takes a lot of time to travel, we are seeing that galaxy how it was when the Big Bang happened. And it is very messy. It's not like us, for instance, we have a nice little orbit around the black hole in the middle of the galaxy. It's like a cracked egg which has been hit hard by a spoon or something. It's very weird, and our human minds just simply cannot understand them very well. Time itself was created by humans. We don't even know if time is an actual thing. We just created it to measure when we should go to work or school. But stuff were there. It's just that time wasn't to calculate when they were there. That's the best way I can put it for you.
Thank you for that. Thank you for that great answer on those enormous questions. And in that answer and in the question, we hear those terms about speed and distance, and you mentioned that, a light year. Can you, for those of us who may not be familiar, what is a light year and how does and that travel? You talked a little bit about this in your previous presentation, how long it would take to travel these enormous distances. You compared that to the speed of the fastest airplane that we have. Can you tell us some more about this idea of a light year, the speed involved perhaps how that compares to speeds as we understand it, even the speed of sound? Can you help us with those ideas?
a light year, let's explain what a light year is. A common problem, or a common mistake, rather, that a lot of us think, even I thought so before I got into space, is that light year is a time, whilst in reality, light year is a measurement of distance, like a kilometer or a meter. A light year is approximately 300,000 kilometers, maybe a little bit more, maybe a little bit less. Now, interestingly, one moment. Yes, as I was saying, interestingly, a light year is the time in which a light travels through space. So, for instance, Bernard star, which we talked about, is 4 light years away from us, meaning a light particle would take 4 years to get from there to here. That's the best way I can explain it to you.
Perfect, perfect. Jaspreet, another great question. Jaspreet, thank you so much. David, with all the study you've done, any thoughts on what are your expectations, or what have you read? How long will we be able to remain on the Earth before it becomes inhabitable? As part of that, perhaps your thoughts on what might be done to make it habitable with all the things that will happen as the universe evolves, universe and stars go through their life cycles.
Unless we manage to find a way to pierce through the sun, there isn't a way for us to save Earth. The only way for us to survive is to be like a tribe. We move around. We move from one planet to another. Once that planet gets close to destruction, we move. We colonize another planet. And so, till eventually we run out. We either A, get destroyed by another space civilization, B, run out of planets to run away to, or just destroy ourselves by some stupid thing that humans do, like nukes.
Perfect. Skeletons, great question. Can you tell us a little bit about atmosphere itself? Skeleton's question, why is the atmosphere on Mars so thin? And what is that itself? The idea of an atmosphere can be the idea of thinness of one atmosphere as compared to another.
Well, an atmosphere is basically the thing that holds on to gases. For instance, our atmosphere is thick enough to hold on to oxygen, carbons, and other types of things, whilst acid gases can escape from our atmosphere. For instance, Venus has a very thick atmosphere, so the acid gases can escape. Now, I don't know what's the exact name to acid gases, but that's what I call them most of the time, so we're just going to work with that. Acid gases are the things that create acid. So, because acid gases cannot escape from Venus, the rain that rains in Venus is acid, literal acid raining on Venus. Whilst on the other hand, Mars, as you said, has a very thin atmosphere. So almost everything runs away. Oxygen cannot stay, acids cannot stay, carbon emissions cannot stay. So you have a meter, a diameter, in which you measure a thickness of an atmosphere. In the middle, you have Earth. On the far left, which is the thick part of the atmospheres, you have Venus, and on the other end, you have Mars and Mercury, Mercury doesn't even have an atmosphere to speak of. So, yeah.
Perfect. And I just love the active conversation, the active dialogue that's going on in the chat. This is part of our extraordinary learning community, and that we do so in our warm, supportive environment where the views on such interesting questions, all the views of everyone are so supported as we share our own. Blazing Pickle asks David, and you spoke about this, as I recall, in your earlier presentation, collision of stars. Blazing Pickle's question, what will happen if two stars collide with each other?
Well, you have two types of collisions. First of all, you have the normal collisions, in which a star hits another star with enough speed to destroy each other, both of the stars. And then you have merging of stars. The merging of stars is when two stars come close to each other at a good speed in which they don't destroy each other. So their cores merge into each other and become one supermassive star, like R136A1. They become strange stars. However, if a star comes in at enough speed and on the right direction, the cores will hit each other, and instead of merging, they will destroy each other. That's the merging of stars for you.
Perfect. Jaspreet is asking such great questions. David, do you have any thoughts on the evolution of consciousness itself, the place of human consciousness, of human thinking in the universe? Such enormous questions. Do you have any thinking on that great topic?
Well, human consciousness, I haven't gone into detail about it ever, but I do know a little bit, a few things. I will try to answer as well as I can. So, consciousness is an important thing in a human's, well, everything in a human's, if you want me to be honest. But it also is kind of a setback. For instance, if we were to send a supermassive spaceship with 4 astronauts to get to the nearest star, to, for instance, Bernard star, it would take them 4 years. Consciousness will hold them away. For instance, someone may consciously think, oh, I miss my family, why did I come here? So they will just give up on the mission, and thus they will give up on humanity. So consciousness, whilst it's good in Earth, and it helps us a lot on Earth, it is a very, very bad thing in space, because it makes a lot of setbacks happen.
Thank you. Again, to students who have joined us late, today we're doing a student presentation. We have the great opportunity for a student presentation.
One moment, sir. I'm going to be back in 5 minutes, sir.
Okay. While David is attending to those matters, again, students have the opportunity for student presentations and student speeches in class. Further information about those are on the Notion page. On the Notion page, you can also see information about previous student presentations. If you are interested, there are further instructions and sign-up forms on the Notion page, as is indicated there. Make sure that you also send me a direct message to let me know that you're interested. On the Notion page under class schedule, you can see some of the upcoming student presentations. No problem. We have about 10 minutes left. We can take a few more questions. Crazy Eight's question, and this was something you spoke to as well in the earlier presentation, the idea of the visual, the visual nature of stars that we see and how that relates to when that light was in time. Crazy Eight's great question. If most of the stars exist thousands and millions of light years away, the state of the stars we see now are millions of years ago? Question mark. That's Crazy Eight's question. Doesn't it make a huge difference comparing to the current state when learning about stars? Again, you spoke about that in your earlier presentation. Can you let us know more about that? Such a great question.
Yes, indeed. Very good question. Yes, it's kind of weird. We are studying how there was, how they was, not how they are. So we may be very mistaken. For instance, if we go right now to Bernard star, as we said, for instance, we take 4 astronauts, put them in a spaceship, and send them straight towards Bernard star. Bernard star may have exploded. We just haven't figured out yet. So these astronauts are going to dust. They're going for nothing. So, yeah, it's kind of weird. Space is kind of showing off what we missed and making us feel very bad about it. But that doesn't mean that we should just give up on space exploration, because Bernard star will not die in a blink of an eye, just like dead. It cannot. We would predict its death. So yes, very good question.
Great question, Crazy. Thank you, David. Smoker from India, thank you for that very clear written description of light year, the distance that light is able to travel in English we would say in 1 year. Thank you for that. And again, Smoker from India.
1 moment.
David, we'll give David a chance to return. That is such a insightful question and observation, Crazy 8, that the very things we are observing today are things that we're actually observing the past in our exploration of the universe, considering the vast distances. No problem. We are looking at a Smoker from India's question. David, what is our current understanding of planets that are, or we expect to be, perhaps inhabitable by humans?
I'm sorry, can you repeat the question one more time?
Smoker from India's question, have we found any inhabitable planets in the universe? Or what's your thinking as to whether we will discover planets that we can live in, or create conditions that we might be able to live on other planets?
Oh yeah, definitely. We found a lot of planets like this. So basically, a star has what we call a habitable zone. So a habitable zone is in a distance in which it's not too far away for the planet to freeze and not too close enough for the planet to burn. That's what we call the habitable zone. And there are millions, if not billions, of these planets that have been found. So yeah, we have found such planets. And unfortunately, agencies like NASA and other space agencies simply don't have the capabilities to, for instance, send a drone to these planets, these far, far away planets. But they are there.
Perfect. Blazing Pickles, great question, and a huge topic in itself. David, have you done any study, any thoughts on this idea, on the idea itself? Your thoughts, does this notion of a parallel universe exist? Multi-dimensional universes. Do you have any thinking on these very broad questions?
Well, imagination is good, so I would love to imagine that there are such parallel universes, and I can't bring you any evidence that there aren't any parallel universes. So I personally like to believe there are, yet I highly doubt they are parallel universes, or there are any parallel universes. So yeah, unfortunately, I think that is just a concept that has been made up by the media, and well, people do like to believe stuff about space, and I did myself, so I don't blame them.
Thank you for that. Arlo, the class is not about science questions per se. In our English classes, we have the opportunity for students to do student speeches and student presentations. The topic today is one on science. It's the second in David's series on the universe. Today, the largest stars, their life and death. Smoker from India. David, I think you talked about this a little bit. The notion of whether time travel is possible, how that relates to the limitation, at least as we understand it, of the speed of light itself. What is your thinking on this idea of being able to travel in time itself?
Well, unlike parallel universes, I can give you evidence on this, on that it is kind of possible. It is said, theorized rather, that if we travel around the Earth at the speed of light, anti-clockwise, so in the opposite direction of the Earth, we would be able to go back in time. Now, how long we stay in that orbit of backwards, light speed backwards traveling depends on how much, it means how much we're going to go back in time. Of course, we haven't tried this because we don't have space travel, but it can. Oh, yeah, and actually, the evidence that I wanted to say is that, for instance, in Mars, in Venus, in other Mercury and other planets, time travels very differently. So time, unlike, for instance, gravity and, I don't know, parallel universes, is flexible. So there can be a loophole, which means that we can travel through time. It's just that we haven't found it yet.
So interesting. We have just a few minutes left. Ed, thank you for sharing that so much. That's so great when a presentation can be of such interest that although we did not first have an interest, a background in it, we can enjoy the presentation. And again, David's presentations are such great examples of how to do a presentation so well. David's slides that he has assembled, the presentation, the content, the presentation of itself is so great and makes this topic of interest to so many, even to those, as Ed indicates, who may not have had a background or an interest in these topics before. Ed, thank you so much for sharing that. And David, thank you so much for doing a presentation that makes these very interesting matters of interest to others. And yes, to students who have joined late, yes, Ninive has so graciously offered, when possible, to record our student presentations going forward. So this will be available once the video is processed. The link to David's presentation, to the video, will be available on the Notion page under Student Presentations. Again, thank you so much to Ninive for that. All right, in the few minutes we have left, let's see if there are any more questions. Scrolling down. Blazing Pickle mentions, David, can you give us any background to dark matter itself? What is this idea of dark matter?
Well, it feels like everything that has dark in its name is kind of mysterious and we can't understand it. For instance, black holes, we don't understand them, we can't understand them. Dark energy, we don't understand them, we can't understand them. So, I don't know. Who knows? Maybe black holes are made up of the same stuff that make up, for instance, dark energy. We don't know. Almost nothing is known about dark energy. However, we do know that, we talked about this in the previous presentation, it pushes pockets of density away from each other. And as it's moving them away from each other, it speeds up the movement of away from each other, the movement in which they are moving away from each other. So it kind of stretches the universe, if you will.
Perfect. And my dearest brings up a term. David, could you give us an idea, the difference between the term astrologist, astronomer, cosmology, universe, the difference between these very different terms? Can you give us that background?
Can you repeat that question, please? I didn't get it very well.
So, my dearest brings up this term that we're familiar with, astrologist. How does the idea of astrology differ from cosmology and astronomy?
I don't know. I've never touched on that. It seems interesting.
So,
I've never.
so I will add to that from an English perspective. An astrologist is a very interesting topic. It's a topic that is very different from astronomy and cosmology. These terms, astronomy and cosmology, refers to the topics and approach that David has been presenting and describing in his presentations. Our efforts over so many years to gather data and present that understanding of the creation, the evolution, our expected the expected progress, the expected evolution of the universe, of the objects in the universe, stars, planets, space itself, that approach. Astrology is a very different topic. Those interested in astrology and astrologists take a look at the organization of the relation of objects in the universe, and their thinking on what can be determined from that. They're both interesting. They're very different. They're both very different. So those terms, astrology and astrologists, those who practice astrology on one hand, and the very different subjects of astronomy and cosmology. And David's interest is in those latter, in astronomy and cosmology. Thank you, my dearest, for bringing up those very interesting English terms. Class is about over. Let's see very quickly. We spoke a little bit about parallel universes, and David's thinking about the possibility or the question of where the idea itself came from. There was someone just sent me a suggestion for a future topic on time travel itself. Again, students are welcome to do a student presentation, to do a student speech or student presentation on any topic of interest. There's information and sign-up forms for that, and of course, as the instructions indicate, send me a direct message, let me know. David, I don't know if you yourself would be interested in putting together a topic on time travel. Again, a great way to do a student presentation is in a group with others. We have had past student presentations, and we will have future student presentations that will do that. When you find others, speaking to the entire class, when you find others with a common interest, perhaps that's something that you would be interested in doing, is doing a student presentation as a group. It, of course, does not need to be just on the universe. So anyone who is interested perhaps on your own or with a group doing a topic on time travel, that would also be a great idea. Let's see if there are any other quick questions before we end class. I think that's it. Great. I think that's it for questions, and we're just a little bit over in class. Everyone, first, a special thanks to Ninive. Everyone, a huge round of applause for Ninive. We had several students asking towards the end of class, students who were not able to join until later, and students are always welcome to join at any time. Thanks to Ninive. You will, all of us will be able to watch David's great presentation today again. Once the video has been processed, it will be posted on the Notion page under past student presentations. This round of applause is for Ninive. Again, this is the most important aspect of our extraordinary learning community, our support for each other. Ninive, thank you so much for that. And of course, our great thanks to David for this incredible presentation. David, before we give you your round of applause, any final thoughts to the audience? What a great presentation. Any final thoughts to the audience?
Thank you all for being patient with me. I know I can be a little bit I stutter a lot in my speaking, so thank you all for being patient with me, and I hope I sparked an interest for you guys in this field of astronomy.
You did so great, and David's presentation, as I said, is such a great example of what a great presentation is like. And David is so humble. David, your presentation was absolutely perfect. Your voice, your presentation were perfect, as was your first presentation. As well as the great information, David's presentation can be an inspiration, a motivation to all of us for all of your ability to do a presentation. As we said, take a look at the Notion page for past presentations. As Blazing Pickle brings up, you all are such unique, special, valuable individuals. Each of you has your own area of interest. You are all welcome to present on the things that are of interest to you. I appreciate what Ed said earlier about when a student such as David does such a great presentation, it develops an interest in others. Emma has joined in that idea. Emma, to David, you've done an amazing job. You've already sparked a great interest in your last, and of course, in this presentation. I encourage others to be inspired, to be motivated by David's presentation, to do your own on whatever your interest may have been. Again, take a look on the Notion page at past student presentations. We've seen topics on English learning. We've seen a presentation by Demonade on the relation. I didn't mention this the first time. I apologize for that. Demonade's great presentation on the relationship between piano learning and English learning. That was a great presentation where Demonade also played great pieces on the piano for us and did a return presentation on that. We had presentation on poetry readings, David's first presentation. Nina's great presentation herself on motivation and stress. Gabriella's great presentation on the English words, type of words, connectors and linkers. Demonade's recent presentation on the new Notion page. That brings up, that was Demonade's presentation on the work she had done to create the new Notion page. That brings up so many of you have backgrounds in technical matters and software matters. That offers the opportunity for all sorts of types of presentations. The idea of student presentations is both topics of interest themselves as well as the important opportunity to practice and develop your skills in English. As we say in the introduction class, the lectures in class, the materials in class is only the beginning. The most important learning occurs as you apply the tools, methods, and techniques that we introduce and discuss in class in your own learning and with other student presentations and student speeches. And again, one of those topics, Cat Zero's presentation on cats and how they improve our lives. So many different ideas, interests that we have in each of us that would make a great student presentation. So a great opportunity to do the most important part of learning, applying what we do in class. That's the great opportunity, not just the terrific information, but the great opportunity to practice the skills, methods, and techniques that we learn in class. And yes, Jaspreet, the links to the recordings. Yes, the link to the presentation will be on the Notion page in the section past student presentations. in the section past student presentations, we keep a list of the previous presentations and where there have been videos. The videos that Ninive makes of future presentations will be listed there on past student presentations. Emma has pasted the direct link to that section of the Notion page. Once Nina's video is processed, that link will be up there. All right, everyone, great class, great class. David, thank you so much for your extraordinary first presentation and your equally extraordinary second presentation. We'll look forward to more in the series. What a great topic, what a great presentation. Students of all levels are welcome. Student speeches offer a less formal opportunity to do that. Student speeches, student presentations, a little more formal. As long as your hardware, your microphone, your computer allows the speaking to be clear, as long as your presentation itself is accessible to all. And I work with the presenters in practice sessions before to help you with that. Yes, students of all experience levels. I am happy to work with you to put together a presentation or a speech that will be suitable for all. I encourage students of all learning levels to do that. And in your recent exercise, I can let you know that you certainly have the ability to do that. I'm glad that sounds of interest to you. Again, everyone, take a look on the Notion page for sign-up forms and more information about doing your own student speech or presentation. And as part of that, make sure you send me a direct message to let me know you're interested. Once again, David, thank you so much for your amazing presentation. Ninive, thank you so much for what you provide by providing the videos so that we can enjoy them again, so that students who didn't see them can see them. Thank you so much for that. David, thank you so much for your great presentation. Your first was so terrific, as was this one. David, thank you so much.
Thank you. I'm gonna have to go now. Thank you all, and goodbye. It was really fun.
Thanks, David. Thanks, David.
Bye. Bye, everyone.
Bye-bye just for now. All right, everyone, thank you all so much. And to those offering their thanks, it's to you, the community, it's to each of you students that the thanks goes. Our extraordinary learning community, our family. It is each of you who have created this incredible place of warmth, this incredible place of support, as returning students have experienced so well, as we discuss so often. A warm, supportive environment, the experience of that is not just something which feels so wonderful, but makes all these things possible, makes an environment possible where students of all levels, that's question, where students of all levels feel experience the courage, experience the confidence to come before the community and offer their personal experience, their background, in the forms of whether it's simply participating on stage for an exercise or coming before the community to do a student speech or a student presentation. It is to you, the community, that the credit goes for each and every time that we are here building and growing this extraordinary environment where we feel the support, the warmth of each other. Let's end as we began with a huge round of applause, for David's great presentation, a huge round of applause for Ninive and the great things that she is doing by recording those presentations. A huge round of applause for each of you. A huge round of applause. As you applaud the community, applaud also each one of you. It is truly each one of you that makes this community the extraordinary place that it is. A huge round of applause for community itself, for courage and confidence that makes every day our extraordinary learning community. Everyone, take a look at the Notion page for the upcoming schedule. Tomorrow, we're going to have 2 great sessions again. As returning students know, I usually teach 2 classes every day, twice a day, 12 hours apart to meet the needs of opposite time zones. Tomorrow, as you can see on the schedule, we will have classes feedback. That will be an open opportunity by voice and in the chat to share your experience of learning in our incredible learning community, our particular approach to learning, the particular techniques that we use, how we approach learning, what we describe in our class principles. We've done this once before, and when we did this prior class feedback, it was suggested that we repeat this from time to time. That has led to doing this again tomorrow. That will be the class feedback sections. We will welcome your comments by voice or typed into the chat. And Emma, thank you for pasting from the Notion page background for doing your own presentation. All right, everyone, great class. This is the time in the chat we say thank you and see you all soon. You each have extraordinary ideas and interests to share with your fellow students. You each have extraordinary ideas and interests within you to share with your fellow students. All right, this is the time that we say hello to those in the bottom of the chat. Jaspreet, thank you so much for your